So at the beginning, thank you so much, and thank you for Dr. Carraro for inviting me to this opportunity. Next time, I hope to see you physically. So before I start my presentation, I would like to thank my student and my colleague, Hani Shakir, Asma, and Ahmed Amar, Dr. Kazim Khalil, Dr. Khalil Yusuf, Dr. Safa Maharan, and Dr. Iman Khidr. The outline of my presentation, at the beginning, I give some background and motivation behind this work, then about the proposed system, the simulation pattern generator, including the design and operation. Do you hear me? My voice is clear? Hello, do you hear me?
You can continue.
Okay, and then giving simulation and measurement result for this part. Later on, I will go to the second part of my presentation, the signal classification and control signal generation, the proposed method and the results, and to conclude my work at the end. So background and motivation regarding the spinal cord injuries in Egypt. According to the World Health Organization report in 2009, more than 700 people suffered from spinal cord injuries in Egypt. This result taken from the Egyptian Ministry Health Hospitals. Among these people, around 70% out of them are males, while 30% were females, and the injured people are between 20 and 30 years old. So this shows that the problem is very prominent in Egypt, and we have to find an affordable solution for these people. The consequence of spinal cord injuries, I think the audience might know that even better than me, but let me just mention. So the immediate loss of voluntary movements and contractile force might lead to significant muscle atrophy and increased immobility, and might lead to body change in composition. And the damage in neurological structure commonly result in partial or complete paralysis. The muscle denervation might lead to decline in skin quality. Several also cardio metabolic disorder, reduced aerobatic fitness, glucose intolerance, insulin resistance, and decrease in mitochondrial functions. All these might lead to gross loss in patient life quality. So that's make me and my colleague think in presenting a global solution, electronic solution for paralyzed and amputee people. And this is just an overview for the proposed solution. We will collect the biosignal from an intact source like EMG signal, or signal from local field potential from peripheral nervous system, or signal from central nervous system, or even from EEG. This signal will be taken to a signal classifier. I'm sorry, I'm talking from the engineering side, so my speech is mostly engineering. I'm sorry for that. But I will not go to in the very big engineering details. So after signal classification, the result will be taken to a control system to either control a functional electrical stimulation for a limb, or even to control prosthetics. At this stage, the motivation is regarding the patient with brachial plexus and proximal nerve injuries. Usually they undergo repair and post-operative electric muscle stimulation of denervated muscle awaiting for reinnervation. So this requires them regular visit to occupational therapy department, which incur them economic, social, physiological, and transportation overhead. So that's clarify the main goal of our present work is to present a handy, cost-effective, and portable patient-controlled electric muscle stimulator. And the device is expected to have the following advantage. First, it should be convenient, effective in decreasing the burden on occupational therapy department. Second, it will give the opportunity for more frequent functional electrical stimulation. At this stage, the proposed system composed of the following. We will use only the surface EMG signal, sensor for that, and then signal classifier, and taking the result of the classifier to the stimulation pattern generator. To further explain the system, let me start by the stimulator pattern generator. The feature of this part, it should be as follows. At first, it should be programmable. Programmable means that the stimulation signal parameter are programmable. We can select it as we need based on the recommendation of the physician. Second, the system is portable, which means that it will be operated by a rechargeable battery. Third, it is non-invasive stimulation. Fourth, it could be remotely controlled and monitored. Fifth, the number of channels can be extended if it is needed. Last and most important, it should be low cost to be affordable for the target patient. Here is the block diagram of the stimulation signal generator. It is powered from 3.7, only 3.7 lithium ion battery. This is taken to the DC voltage generator, the circuit which generates the required voltage to operate the driving circuit and the microcontroller. And here is the block diagram of the DC level generator. Since we are generating plus minus 60 volt, so that we use a kind of boost converter to generate at first 30 volt, then taken to voltage doubler and inverter to generate plus minus 60 volt. This will fit the driving circuit. There is another path for boost converter to generate only 5 volt that will be used to supply the microcontroller. At this stage, we use off-shelf component to design the boost converter and the voltage doubler and the inverter like this. The stimulation signal generator itself, it is based on microcontroller. We use the power of microcontroller in generating the stimulation signal with the required stimulation parameter. And the stimulation parameter are input to the microcontroller. The microcontroller itself, it generates uniphasic signal, so that we use a kind of subtraction circuit to generate the biphasic signal. And the stimulation current itself is controlled by a fourth knob here, where we can define the stimulation current to the patient. This is just the timing diagram of the stimulation signal, and the parameter that we input to the microcontroller, including the pulse width, the burst on, the burst off time, and the stimulation current amplitude, in addition to the stimulation session time itself. Okay. Before going to the measurement result, we did some simulation to see after some time the DC voltage generator will be ready to supply the circuit. As we can see here, it needs only around 10 milliseconds to be ready to supply the driving circuit and the microcontroller. Also, we did some simulation to see the ability of programming the timing parameter of the stimulation signal. So all what we see here is just a simulation result. The system itself, I mean, the stimulation signal generator is designed and fabricated on printed circuit board and tested in our lab. And here is just sample of the measurement result to show the ability of programming the pulse width and the burst on and the burst off time. This is just a sample of the measurement result. In addition to that, we could also program the stimulation current, and this, the measurement result, we show that it showed us that we can also program the stimulation current. Of course, the stimulation current is programmed through programming the stimulation voltage itself. We can increase the voltage up to plus minus 60 so that we can select the required stimulation current. The stimulation current itself is very important parameter, so that we did an overall evaluation for the stimulation current of our system. And the results show that our system can generate up to 50 milliamps that can feed an impedance up to 1.1 kilo ohm. Lowering impedance means that we can generate more stimulation current. Lowering the stimulation current than this, we can feed a higher skin impedance. And we know that the patient, they are different in terms of the skin impedance. But at this stage, we are limited to 50 milliamps. Later on, if you would like to have more stimulation current, we can do it in the upgraded version of our system. So the stimulation signal generator as a part, it could be used individually to make stimulation at home, for example, or whatever, or it could be integrated with the other part of the system to provide the patient-controlled muscle pacemaker. So the second part of my presentation related to the signal classification and the control signal generator. So the signal classification here, we rely on the artificial intelligence on designing this part, and the input is just the surface EMG signal. So utilizing the surface EMG signal with machine learning are very effective in gesture classification. The acquired signal is utilized by machine learning just to generate the this classification model. And this is just the block diagram to show the technique we use for generating the machine learning based model. We have acquired the signal, then doing some signal processing to extracting some feature, and this feature is used to generate the machine learning based model. The focus in this stage is to designing a highly accurate artificial intelligence based model and efficient signal processing. The featureless deep learning technique, which we call conventional neural network, is adopted due to its advantage over the classical approaches. To train, test, and validate the system, we rely on Ninabro database 5-E2, and we picked 17 hand and wrist movement to make our model tested, tested and verified. The signal are sampled with the sampling frequency of 200 megahertz. This is the block diagram of the proposed method. At the beginning, we load the EMG signal, making some signal processing like fast Fourier transform, making guarantee that the signal, the sample contains 1000 points. This is the required. And then we segment these 1000 points to overlapping windows. Then we split this data into 3 parts. One part used for training the system. Second part is for validation, and the third for training. These are the 17 movements we used in training our system. And here is the confusion matrix, the result of our system. As we can see here, the accuracy achieved by our method reaches around 99.64%. Of course, some movement here can be classified 100%, and some others less than this, of course, like 97%, but the average is around 99.64%. This means that the proposed model here is very promising and could be used to be integrated with the simulation signal generator to generate the fully patient-operated electric muscle stimulator. In conclusion, a portable and low-cost electric muscle stimulator has been presented. The stimulation signal parameter of the proposed system are adjustable within a specified range given by the specialist from the medical side. The device also is capable of providing stimulation current up to 50 milliamps at this stage to feed a load resistance of up to 1.1 kilo ohm. The design has been fabricated and tested in the lab at this stage, and the measurement results agree with the desired specification. The system is designed and implemented using off-shelf components. In addition to the stimulation signal generator, we also developed artificial intelligence-based gesture classification model, and the result of the AI-based gesture classification model reaches around 99.64%, which is high compared with the similar method. This is the end of my presentation. Thank you all. And also, I would like to thank the STDF Egypt for supporting this research. Any question or comment is very welcomed. If you cannot reach me online, please send the question or comment to my email. Thank you again. And I would like to thank Professor Carraro for inviting me again. Thank you all.